Alright, last couple examples here. Again, we're dealing with systems of equation with the elimination method. This one's a little bit tricky because to get opposite coefficients like we were talking about, I can't just multiply one of the coefficients by a number to get the other one without having to use some fractions or something and be really creative. And so instead what I'm going to do is try to multiply both of the coefficients to get a least common multiple. I'm just going to choose the x's. You can really choose the x's or the y's, it doesn't matter. But what I'm going to do is go with the x's. I know the least common multiple of 3 and 5 is 15. And so I want to get a positive and a negative 15. It doesn't matter which one is which. And so I am going to take the top equation and I am going to multiply. I'm going to use a positive 15 on top. So let's multiply by a 5 there. And the bottom equation, I'm going to multiply by a negative 3. Okay? Positive 5 on top, negative 3 on the bottom. If I do that, 5, and these have to distribute to everything. It's the multiplication principle of equality. So 5 times 3 is 15. 5 times negative 6 is negative 30. 5 times 2 is 10. Then the negative 3 multiplies to 5, that's negative 15. Negative 3 times 4 is negative 12. And negative 3 times 1 is negative 3. And now when I add the equations together, my elimination method, the x's drop out, they're opposite terms, or opposite coefficients. We get negative 42y equals 7. And if you divide out the negative 42, 7 over 42 is 1/6. So you get y equals negative 1 over 6. Okay. Now, I also need the x value. So if I take this y value, I look at the two possibilities to plug it in. I don't like the bottom one because I get 4 over 6, which is a fraction. But if I plug it into the top one, a 6 over 6, it eliminates a fraction. So I'm going to go ahead and do that one. So I'm going to take 3x minus 6 times my answer equals 2. Let's do a negative 1/6 in there and simplify. So we get 3x, double negative makes a plus, 6 over 6 makes a 1. Subtract the 1, 3x equals 1, divide by 3, and you get 1/3. So again, final answer is going to be the combination of those two numbers in an ordered pair, also contained in a solution set. Okay. All right, last example. This one's going to be a little bit different. This one is going to contain 3 equations and 3 variables, and yes, you will see larger systems throughout both section 8.1 and the following sections. Okay, so we are going to see some of these bigger systems. Now if I add an equation, I need to add a variable in order to solve it. So these are going to be 3 equations with 3 variables, and we're going to introduce the variable z as I write this out. Okay, we're introducing the variable z into the equations. Now, with the previous examples, we had 2 lines, and the solution was their intersection. Now what we're going to have in 3 variables, that's a 3-dimensional figure, we're going to have 3 planes that all intersect at a point. Okay, the point is going to have 3 coordinates, x, y, z, and so that's there's lots of different ways to configure 3 planes, but if they have a single point, then they all intersect at one point. Okay, so again our goal is to eliminate variables, one in particular. And as I look at the list of variables here, the coefficients, I like the z's to eliminate here because I already have a negative, and having a 1 on this z makes it easy to multiply up to the other coefficients. So I'm going to just take the first two equations and try to get their coefficients opposite on the z. So of course I need to multiply the top equation by 2, and that will create a 4x minus 6y minus 2z equals 0. That 2 distributes to all four terms. The other equation I don't need to change, so I'm going to leave that the same. And when I add those up, the z's will drop out. I'm going to get 7x. I'm going to get, what's that, minus 4y equals 2. Okay, good enough. Now I'm going to combine, so what I have is an equation with two variables now. In order to solve that, I really need a second one, and I'm going to create a system of two equations. So I need a second one just like this with no z's. I can have x and y though. So when we're looking back at the original equations, I can't combine the first two, I've already done that. So I'm going to take the first one and the third one. It just has to be a different combination. And so the first and the third, to get the coefficients opposite, I have to multiply this first one by 3. Okay, multiply by 3. 3 times 2 is 6. 3 times negative 3 is negative 9. 3 times negative 1 is negative 3. And 3 times 0 is 0. The other equation, oops, I guess I didn't really need to rewrite this. X plus 5y plus 3z equals 2. Okay, so I'm looking at those two equations, and when I add them together, again the z's drop out. The x's are 7x, there's minus 4y, and equal to 2. Interesting. Now when I take these two equations, I'm going to put them into a new system. So I'm going to take the top one, 7x minus 4y equals 2. Okay, that's this guy right here. And then I'm also going to take this guy right here and create a system of two equations. Now, what you probably are noticing is that they're the same equation, right? That's not always going to be the case, but sometimes it is. If they're the same equation, then when I add them up, well, actually, if I add them up, I don't eliminate a variable. So I need to eliminate a variable. So what I'm going to do is I'm going to change the signs on one of the equations. Change the signs on this one. That's basically multiplying by a negative 1. And when I do that, negative 7 plus 7 makes 0x. Negative 4, or sorry, positive 4 minus 4 is 0y. And over here I get a 0 also. And that makes the left side all cancels out, and I just have 0 equals 0. Well, we saw a few videos ago that we had a false equation without variables. Here I actually have a true equation. Oops. This is a true equation. And in a true equation, we actually have an infinite number of solutions. Most likely these three planes intersect in a line or in another plane. So this is a true equation with an infinite number of solutions. Okay? And then finally, if you needed to categorize this system, this would be one of those consistent systems because it does have solutions. Okay, it also has yeah, an infinite number of solutions. That's correct. Okay. All right. Very good. I think we'll do one more example in another video, just to show you another example with the 3 variables.